Okay, first, I'd like to thank the organizer for this opportunity to talk, and thank you for watching this video. In this presentation, I'll be talking about the use of GCTA-GREML to estimate SNP-based heritability from GWAS data. We have three modules in GCTA. The first module is mainly about heritability estimation, genetic correlation analysis, and phenotype prediction. In the second module, we have method to do genome-wide association analysis, and in module number 3, we have a couple of other methods. So in module number 1, we have methods to compute genetic relationship matrix to estimate or partition genetic variation, to estimate dominance variance or variance explained by chromosome X. We can run genetic correlation analysis or phenotype prediction analysis using BLUP or summary data-based BLUP. We also have a version of Huysman-Elston regression implemented in GCTA. In module number 2, we have a couple of GWAS methods, and there are two mixed linear model-based GWAS tools called MELMA and FastGWA. So if your sample size is not so large, you can use MELMA, or MELMA leave one chromosome out. If your sample size is as big as the UK Biobank or even larger, you can use FastGWA or FastGWA GLMM if the phenotypes are binary. We also have COJO and MT-COJO for summary data-based conditional analysis, with COJO to do condition analysis conditioning on SNPs, and MT-COJO for condition analysis conditioning on traits. We have also included gene-based test methods such as FastGWA and ACAT. In module number 3, we have GWAS simulator to do GWAS simulation based on real genotype data. We can do PCA or PC projection if your discovery GWAS data set is too large. And we can also compute FST values for genetic variants, inbreeding coefficients for the individuals. We can run LD score computing or to find LD friends for a given set of variants. We also have a version of GSMR implemented in GCTA to run Mendelian randomization analysis. So the main character today is GCTA-GREML. There are 2 steps to run GREML. So the first step is to create a GRM. Here is a command to run the analysis. We tell the program to reading a genotype file in Plink format. We tell the program to run the analysis on the autosomes, and we also have options to include or exclude a specific set of individuals or variants. If your data set is big, then you can parallelize analysis onto each individual chromosome. In this example, we can separate analysis on chromosome number 1. If this is still too slow, like the analysis in the UK Biobank, you can further divide the analysis or the computation on chromosome 1 into different parts. Here, we divided the analysis into 100 parts. And once all the parts are computed, you can simply use the command cat in Linux or Unix shell to merge all the parts together. You can further then merge the GRMs for the chromosomes into a single GRM. Once you have the GRM, then you can run a REML analysis by typing this command, basically the flag dash REML to input the GRM and the phenotype file. And we also have other flags, for example, to include a specific set of individuals or some covariants. In this case, we have 10 PCs included as covariates. If your data come from case control studies, then you can specify the prevalence of a disease in the population to convert the estimate of SNP-based heritability from an observed 0-1 scale to an unobserved underlying liability scale. We also provide an option to run a genotype by environment interaction analysis, which is this one, --G by E. So you can tell the program to run a REML with this flag to input the environmental information and then ask the program to run a log like a ratio test for the G by E component specifically. So you can also run a GREML analysis with multiple components. In that case, you can basically stratify the variance by different information. For example, you can divide the variance into different chromosomes or gene regions or intergenic regions or minor allele frequency or LD scores of the variance. So basically, the variance can be divided in many different groups, and then you run a REML, a GRM computation for each group, create lots of GRMs, and then fit all the GRMs together in a REML analysis to partition the genetic variance into different groups of variants. Here is a very specific example. This method called GREML LDMS is specifically designed to estimate SNP-based heritability from whole genome sequence data or imputed data with rare variants. There are 4 steps. In the first step, you will need to compute the LD scores for the variants. You can then stratify the variance by both minor allele frequency and LD scores of the variants. You then compute a GRM for each variant group by the following commands. And finally, you run a REML analysis with all the GRMs fitted together. And of course, you can include the covariates in this kind of analysis. We also provide options to do analysis to estimate non-additive genetic variance. Here, in this case, dominance variance. So you may need to start with a computation of a dominance GRM together with an additive GRM, which is a default for the GRM I mentioned before. So you have 2 commands here, one to compute an additive GRM and the other to compute a dominance GRM. Once you have the additive and dominant GRMs, you can fit them together again in a REML analysis to estimate additive and dominance genetic variance for a trait. We also provide you an option to do genetic correlation analysis, which essentially is a bivariate GREML analysis. So the command is actually very simple. You tell the program to run REML bivariate analysis with the input of GRM and the phenotype file. I call this balanced design because in this analysis, we assume you have two phenotypes measured on exactly the same set of individuals. But in some cases, the design can be unbalanced. For example, in this case, if I want to estimate the genetic correlation between males and females for human height, I treat the male height and the female height as two different phenotypes. So in this case, I have phenotypes, male height measured on males only and the female height measured on females only. So if you input a phenotype file like this into this bivariate GREML analysis, the program can also estimate the genetic correlation, so which is essentially the male and female genetic correlation. I guess this is the end of the kind of tutorial talk, but I also want to take this opportunity to mention a few frequently asked questions. For example, a commonly asked question is the sample size required for a GREML analysis. For common variants, I would suggest a sample size of at least 5,000. Of course, it would be better if you can have more. And for genome sequence data or imputed data with rare variants, I may suggest tens of thousands. And in terms of computer memory requirement, we have provided equations in our website to approximately compute the computer memory required for GRM computation and REML analysis. So another question is about whether we can apply GREML analysis to family data. The answer is yes. We often have two strategies. The first strategy is to remove one of each pair of individuals with estimated genetic relatedness larger than a threshold, for example, 0.05. Another strategy would be to use a so-called big K and small k analysis. So it's essentially a multi-GRM analysis with one dense GRM and another sparse GRM to estimate SNP-based heritability and pedigree-based heritability simultaneously. In terms of this relatedness threshold, we often use 0.05, but in real data applications, we don't really see too much difference if we use 0.025 or even 0.1 for GRM computed from HepMap3 SNPs or a similar set of common SNPs. So we also have feedback about issues related to convergence, or sometimes the estimate is too big or too small. For example, in the REML iteration, the estimate can hit the boundary of the parameter space, which is 0 or 1. In this case, we think that it's likely because the sample size is not large enough. We know the variance of the estimates is inversely proportional to sample size squared. So if the sample size is too small, the estimate varies a lot, and by chance it can hit the boundary if the true parameter is either too big or too small. In case control studies, this may also indicate that you have some technical differences between cases controls and often more stringent QC need to be applied. Another issue is that the REML analysis is not converged. Unfortunately, we don't have a universal solution to this issue yet. It's often to do with errors in the data or analysis script, and sometimes you may just have to increase the sample size. Yeah, the other question is about whether we can use GREML to estimate the variance explained by a subset of variants. The answer is yes, but the estimate will be inflated if the SNPs are selected from the same data. So one suggestion would be to select SNPs from one data set and to do the estimation in another independent data set. And we also have flags in GCTA to estimate the effect size of the covariates, or to estimate the fixed effects. And this is sometimes useful if you are interested in testing the association between a covariate and the phenotype, conditioning on the polygenic background. And finally, we also have an option to do prediction to predict the random effects. So here is an example. We can use this REML REML predict random effect to output all the blob solutions for the total genetic values of the individuals captured by the SNPs. We can then use this option blob SNP to input the genetic values of individuals and then to convert individual blob solutions to blob solutions for the SNPs. And then you can use these SNP blob solutions in Plink to compute a polygenic risk score, or PRS, in an independent sample. So it's essentially a sort of individual level data-based blob analysis. I think this is the end of my presentation. So if you have any question, you can visit our website or drop me an email. And thank you again for watching this video.